so thank you for your comments, and I will start now with my course. And the material, okay, now it's gone. Maybe, yeah. What I want to tell you today is about the ideas coming from functional analysis. But functional analysis, as I point out in this ideas and thought file, is just the continuation of linear algebra. So if you remember, linear algebra, depending on what course you took, is the theory of vectors and matrices. So you may have learned that there are column vectors, there are matrices acting on column vectors, matrices of size m times n map Rn into Rm. So if somebody is giving a 3 by 5 matrix, you can of course apply it to a matrix, to a vector, a column vector of size 5. And you're doing it in a usually funny or particular way. In the same way also you're doing matrix multiplication. So you're saying, well, a matrix, as it is for MATLAB, is just a collection of column vectors. So if you have one matrix applied to another, it's one matrix applied to a collection of column vectors. Of course, this is only possible if the format fits. So if somebody is asking, can I multiply a 3 by 5 matrix with a 7 by 8 matrix, you would say, no, that's not possible. So I call it the domino principle. So a 3 by 5 matrix can be multiplied with any 5 by anything matrix, and the outcome is a 3 by anything. And this is the usual way of your learning how to do it. However, in reality, you may have a linear mapping and you do not know the matrix. Then, of course, you have to apply it to the unit vectors. So this is actually what I did when I was showing you the plot of the FFT matrix. FFT of I of n is FFT multiplied, applied, or the linear procedure FFT applied to a collection of unit vectors. Recall, the unit matrix is just first, second, third unit vector put together in an n by n scheme. And so if the routine is applying column-wise the entries, then you know how to get the matrix. You take just the linear mapping applied to the collection of unit vectors and applying the matrix multiplication. The matrix to the 5th unit vector just gives you the 5th column of the given matrix. So I've described this in some of the files, but we will also do it in MATLAB later on. So, well, the idea is if you multiply a matrix with a unit vector, you get the column with this corresponding number. If you put a 3 into the column, so instead of unit vector number 5, you have 3 times unit vector number 5, you will get, of course, 3 times the column vector. And if you're having a general matrix, a diagonal matrix, then you will get a linear combination of the column vectors of the original matrix. So this is kind of the link between linear mappings, we will do it several times, and matrices. Once you have a matrix, you can do linear combination of vectors, namely column vectors. If you have an abstract linear mapping and you choose a basis, you can get the matrix by applying it to the unit vectors and describing in the same basis. So this is more or less what you do in linear algebra, and the key terms which I also have here in this file is the notion of, so we can do linear combinations, let's say it in this way. What is a linear mapping? A linear mapping is something, a mapping from one space to another, which allows to do linear combinations before or after the application of the mapping. A good example, and I will come back very often to the polynomials, is differentiation. If somebody has learned very early on how to differentiate a polynomial, you learn maybe not that it's putting a tangent to the curve, but first it's taking the exponent and pulling it down and then reducing the exponent. So x to the 5th differentiation gives x to the 4th, but you pull down the first. So it's 5 times x power 4. And how do you differentiate the polynomial? You do it term by term. And you take the constant factor out. And so the differentiation is clearly a linear mapping on the set of polynomials. From every given polynomial, the differentiation is another polynomial. And later on, we will be interested in operators which are linear and which commute with translations. And this is also true for the differentiation operator, because everybody knows if you take a curve and you differentiate it, you are determining the tangent. What does it mean to shift a curve? We have seen it yesterday with the GeoGebra. It just means that you're taking the same graph and move the basis points. Now clearly, if you are taking a tangent on a curve and you move the curve, the tangent is just moving around. So you have the same differentiation, the same steepness, but at a shifted place. So differentiation is one of the prototypical operators which can be applied to the linear space of polynomials. We all know that you can add polynomials, you can do linear combinations. That's how they are built essentially from the monomials. And we have differentiation as one of the possible operators which commute with translations. And this is one of the key subjects of linear system theory. Now, the next thing, okay, now I think I switched, but not on purpose, to the functional setting. Sorry. Yeah, I come back to the original. So the next term that you can do once you know what a linear combination is to ask, well, if somebody gives me a linear combination, can I determine the coefficients? Of course, you have to know the basis vectors, but if somebody gives you in R3 vector x1, x2, x3, of course, in the standard basis, you know the coordinates are x1, x2, and x3. But in a more abstract setting, you would say, well, any orthonormal system can be used. You just project the coefficients into the basis vectors, then you get the coordinates. If somebody is giving you an oblique system, which means you have a general invertible matrix, then you have to think a little bit more carefully, and you will find out that the inverse matrix is helping you to determine the coefficients. We don't have to do it here. So linear independence is the keyword here. Only if vectors are linear independent, if there's no redundancy built into the system, you can determine the vector the coefficients from the linear combination. The other thing is, of course, if you have a lot of vectors, some vectors, let's say you have 5 vectors in R12, and you try to build all the vectors, you will see they're not enough. So the question whether a system of vectors is spanning. So a system is called a spanning system if all the linear combination, all the vectors in your vector space are obtained as linear combinations. So again, back to the polynomials, I like to talk a lot about cubic polynomials. We all know that you can use 1x, x squared, and x third power as a standard basis, the monomial basis. And if you take all the linear combinations, you're fine and you're having all the cubic polynomials. We will study, I would suggest on Tuesday, what happens if you, for example, you shift these bases. So what happens if you shift everything by 1? You have 1, constant 1 is left invariant, x goes to x minus 1, x minus 1 squared, x minus 1 second power. And the question is, can you still build every polynomial, every cubic polynomial from these things? I leave it to your fantasy and your considerations to think whether it's still a basis. Also, it means that then if it's a basis, probably because shifting polynomials is a linear operation. And what is the matrix? What is the inverse operation? what is the inverse matrix for this operation. I really think that you should try to think about it, not in order to build up frustration, but in order to appreciate the answer that I will try to show you next time. Okay, next step is we are going to do signal processing, and the main topic from my point of view will be signal processing for continuous non-periodic signals. So we are not so much interested anymore in the finite dimensional case, except for the computability. So MATLAB will not allow you to feed any continuous function. Whereas, of course, you have seen in the STX program, I can look at the spectrogram of a continuous sound signal. So it's not unphysical, but one has to understand the transition between continuous and discrete. So today I want to dive into the world of continuous functions, which are periodic and non-periodic. The periodic part is more for historical reasons, whereas the non-periodic part is, for me, the beginning of the story and the place where you can appreciate the role of functional analysis. Now, what is functional analysis not by formal definition, but intuitively? It's the theory of infinite dimensional spaces. That sounds terrible and mystification but we are not saying that this is a theory of spaces which have an infinite basis. Not at all. It's just a counterpoint to the statement of finite dimensional. So in fact, we should think of it's the theory of not necessarily finite dimensional spaces. So essentially, it's another way of looking even at linear algebra, but say, well, what can I say about the space without making use of a concrete basis? After all, we have the problem that if somebody is choosing a basis, then another person is choosing another basis. And we have this kind of important, but sometimes nasty problem of changing the basis. You are looking at rotation in the wrong coordinate system, your rotation along some axis in 3D space, but you write it, of course, in standard coordinates. How can you appreciate that one direction is left invariant? That's an eigenvector. It doesn't change neither direction nor size. And so you have the whole business of eigenvalues, eigenvectors, and so on, which is very important, but at the moment not in the scope of what I want to explain today. So once more, we're talking for signal processing of continuous functions. We need certain signal spaces or function spaces or vector spaces. Vector is to be understood in an abstract way. Vector is just some objects that you can add. And we are trying to do it in such a way using, of course, established mathematical tools, some of them almost 100 years old. We are using this without use a reference to a basis. I would like to add that there are 2 or 3 other reasons why one should look at these things. Also in differential geometry, I have learned early on that people try to argue in a coordinate-free way. Why? Because whenever you describe terms through coordinate systems, you have to say, well, let's say if a surface is flat at some point, given some coordinates, and then you have to say, well, but if somebody is giving you the same surface described in other coordinates, is it still smooth according to the same definition? And that requires some cumbersome computations, which are usually elementary, very long, and very boring. So I try to avoid now in the context of functional analysis or function spaces, the use of coordinate systems. The other thing is that, of course, sometimes it's not so easy to build a basis for a function space. Sometimes you argue that if you're familiar with Hilbert spaces, which is kind of the infinite dimensional analog of the Euclidean space, so you can say, well, Hilbert space is something where geometry, orthogonality, orthogonal projections, all these things make sense. And in a Hilbert space, if it's separable, so kind of, if it's not too big, it's maybe infinite, but not too big, then you always can find a lot of orthonormal bases. And then you work with these orthonormal bases as if they were orthonormal bases in finite dimensions, with the exception that, of course, you have to know how to handle infinite sums. So instead of a finite linear combination, you're allowing infinite coordination, infinite summations, which are called series. And these series behave very much like the finite dimensional orthogonal expansions. Now, because we are doing Fourier analysis, one should mention that the most important and very thriving example, which was stimulating the theory very much, was the theory of Fourier series. So you have to think, Fourier was, I will give more details in, or put a link to a talk that I gave some years ago, about 200 years of Fourier theory. So Fourier was developing or suggesting the theory of Fourier series, the development of periodic functions into pure frequencies, at that time written in terms of cosine and sine, and following Euler's rule, nowadays, of course, using exponential function with complex exponents. So he was suggesting to develop every periodic function into an infinite series using pure frequencies. I would say it took almost 100 years until mathematicians had developed enough integration theory, concepts of functions, and so on, until they were saying, oh yes, it's just what you have to do is take the space of square integrable periodic functions. So we'll say, take functions wrapped up on the unit circle, so they are not periodic patterns on the wall, but there are really graphs on the circle, and assume that this function is such that it's finite energy, which means that you take the function, real or complex valued, take the absolute value squared and integrate it over the full period. And then this function space is an infinite dimensional system, or an infinite dimensional vector space. It has a scalar product. The pure frequencies are a orthonormal system, and they are even complete, which means that every function in this L2 space can be represented as an infinite sum. It's a one-to-one. The length of a vector is this integral squared is just the length of the coefficient vectors, which is the infinite square sum, and so on. So everything is very, very nice. But already here, the continuous variables make that you can have infinitely many dimensions. Again, this doesn't, in this case it's true, but it's not emphasizing that you have an infinite orthonormal basis. But in the more general situation, you should just think, we don't want to make use of it. Just take L1 space, LP spaces, other function spaces with other norms, and you will find out that these spaces may not have a basis, and we will use a lot the concept of Banach spaces, which I will explain also in a moment. They're kind of vector spaces which may be infinite dimensional and which have the property that Cauchy sequences are convergent. So they are behaving like Rn with respect to metric properties. Somebody says, I'm computing things and they are more and more close to each other, then it's a Cauchy sequence, and that Cauchy sequence will have a limit. And Per Enflo was showing in '73, so this was one of the exciting messages of new results in mathematics when I was a student, and it was saying, oh, there are Banach spaces who are so nasty that there is no basis. And that roughly means, well, if somebody tries to build a basis, he fails either because he doesn't have enough vectors, so he will not span everything. But whatever you do in this space, if you try to have a system, if you try to make enough elements, you will have problems with the uniqueness. So in this sense, it's not possible to find a basis in this particular nasty, I would say, pathologically constructed space. So ever since that time, it has been an interesting question, and a lot of experts have developed a huge theory You can look up the book of Singer, which is a couple of 100 pages long, about bases in Banach spaces, which space has which bases, and so on and so forth. We will hear maybe later on a little bit about Hermite functions, because they are very nice with respect to the Fourier transform, but otherwise we will not handle very much the problem of existence of bases in Banach spaces or so. So actually I would like to stop here for a little moment and to switch over to the course notes. So this was kind of a general indication about the theory of functional analysis, why I think it's necessary. Yeah, maybe one argument that I should take from here. Definition number one: if you have such a space of signals, vectors, images, objects, if you want sound signals or so, if they're of the same kind, you have a linear structure, so you can build linear combinations. I think even GeoGebra is a good example, because you can say, well, you have one function p of x, I don't know, a Gauss function, another function which is sine of x, and you dilate this function, and then you say 3 times one function plus 4 times the other function. And MATLAB also, but GeoGebra knows how to plot these things. So it doesn't have to be coordinate vectors. It can be any object which is in a linear space where linear combination makes sense. And now, if we want to say we can have build infinite sums, we have to be able to know what does it mean? What is the meaning? And the answer is, well, if this infinite sum is convergent, which means I take the first 500 terms, I have something, I add 20 more, I get almost the same. And even if I have 5 million terms, it's practically not changing anymore. Then I have to express what is the change from 500 to 5 million or so. And I need something which I call a norm, or which is the standard terminology, a norm, or I call it a size measurement compatible with the linear structure. Maybe you take a look at the definition number one while I'm drinking a glass.
Sorry, we cannot see the PDF that you're showing, I think.
Oh, thank you. Please oh, yes. So there was not much until now, but do you see now definition one, or was it the wrong one?
Yes, it's visible now.
Okay, thank you very much. Yeah. So it's something that you find in probably I would put it in the appendix of the course notes, but in my functional analysis course, I also have seen it in the notes of Professor Bölzkay and so on. So what is a norm? It's a standard definition. It's a size measurement, and it has 3 properties. The first one, if something is the size is of course positive, so you're assigning to each vector a number which is non-negative. And of course, if the norm is 0, if you say, well, it's of size 0, it should be the 0 element, so the neutral element in this additive structure. It should be what is called homogeneous, which is property 3. So if you say x plus x, or normal people would say 2x, it should have the length 2 times x. If you go in the opposite direction, minus x, you should have the same length of the vector. And if you continue this property for rational numbers and then take limits, so if it's a reasonable way of measuring, it should be homogeneous in the size of, for any number, and this special letter k is standing for Körper, the German word of field. So this is just one symbol used for real or complex numbers. So think of maybe k being complex, and it's more interesting. So if you multiply a vector by the complex unit I, which is of course size 1, it doesn't change the length. Actually, if you rotate by multiplying with any element from the unit circle, you don't change the length of the vector. And in terms of kind of usefulness or how frequent it is used in our arguments, you will find the triangle inequality the most important thing. And it's called simply triangle equality, saying that the straight line from 0 to x plus a, so think of arrows now in the plane or so, is of course not larger than if you make a deviation and you first go to the end point of x and then you walk along the vector from x to x plus y, which has of course length y. Okay, so this is the concept of a norm. And of course, once you have a norm, you have also a metric structure, which simply means, well, somebody is giving you two vectors and you would like to know how far away are these vectors. And then, of course, you say, well, I take the difference of the two vectors. And if the difference is 0, then they are equal. And if not, I can at least say they have similar orientation and direction or so. So yesterday and in my collection, one of the easy files of called comp norm is take the Euclidean norm for vectors that of course satisfies all these properties. And if somebody is giving you two vectors, then it says, well, first I look kind of thinking of property number 3, whether they have equal lengths. If they are not equal lengths, maybe I normalize them. And then I'm using the normalized vectors. So you divide a vector by its length. So it's clear that if you choose lambda to be 1 over the norm of x, then of course the normalized vector, again, the vector of the form x divided by norm of x, is having the length. Well, the lambda is 1 over x times x, which is 1. So it's clearly normalizing just means putting everything to norm 1. We will very often talk about normalized vectors in Rn, which are real vectors in MATLAB, or signals which have a 2 norm equal to 1. We will have a lot of concrete examples. Now, a vector space equipped with such a measurement of size, which also means a measure allowing to measure distances, is called a normed space. Now, if somebody is giving you a vector space and kind of in search for a basis is asking you, well, maybe I can get the basis. Maybe just think of R3 with Euclidean basis. When is a set called total? And in the finite dimensional setting, you would just say, well, if every element is a linear combination, so if the set is spanning the space, then everything is fine. Now, in the case of infinite dimensions, you must say, well, finitely many vectors never can or may not span everything. I mean, that would, to talk about only finite dimensional linear combinations is going in the direction of algebra and logic and Hamel basis. That's a difficult territory, but not, I think, not relevant for applications and definitely not for us here. So a set is total if its closed linear span coincides with the normed space. Without going too much, that's the difficulty of the display and the way of presenting. I have to talk a little bit too much, but so if you remember maybe the theorem of Weierstrass. The theorem of Weierstrass says, well, let's look at all the continuous functions, maybe on the interval 0 to 1 or -1 to 1 or any interval on the real line, for example. And then you say, well, I can look at the polynomials of any degree. So 1x, x squared, and so on. Infinitely many such terms. And then the question is the set of monomials, also these powers, integer powers of x, from 0 to infinity, are they a total set in the vector space of continuous functions with the sup norm? This is actually an example that we will use a lot later on today. And then the answer is yes, that's exactly what Weierstrass theorem says. It says, if you're giving me any continuous functions, and you might think, draw a graph, and then you're saying, I'm giving you an epsilon, or you're giving me an epsilon, then I would say, okay, I mark an epsilon strip above and below the graph of the function. And then if Weierstrass theorem is valid, I must be able to show that there is a polynomial, maybe of a very high degree, maybe with very strange coefficients, but that polynomial is living within this epsilon strip of around the given function. Now, we will see that the same task for trigonometric polynomials, so for linear combinations of pure frequencies, is rather easy to deal with. But in the case of Weierstrass, it's a very nice and very important mathematical result, however, which is non-constructive. So it's not in the usual way of proving it, it's non-constructive. There was an approach, or there's an approach going back to Bernstein, who is one of the founders of approximation theory, and he was able to show that so-called Bernstein polynomials can be used for this approximation procedure, so that would be a constructive approach. So to claim that something is total can be either claimed kind of by avoiding a scandal, assume it was not total, then we would have a contradiction to some established mathematical fact, or we would do it in a constructive way. I'm, of course, whenever possible, trying to show how things can be done constructively. Now, since we have already here the main definitions, let me go through this definition also. What is a Cauchy sequence in, okay, it says usual facts. In a normed vector space, I will expand this definition or make sure. It just says, well, if you're, I'm just saying it in words now first. If you're giving me any epsilon and you're saying, well, I want to determine something up to precision, maybe 5 digits, if it would be a real number or so, then I would say an approximating sequence, a so-called Cauchy sequence, is good enough as long as I take a sufficiently large index. So I might say, well, you are giving me this very small epsilon that's a bit nasty you're challenging me. But if I tell you take n equals and 0 equals 10,000, then you can pick 2 indices. One is maybe 10,001 or 10,300, and the other could be 5 million, or any pair of arbitrary far away indices which are bigger than the number I gave you. I could tell you, please look only behind 10,000 and measure the distance of the two, and they would always be less than this given epsilon. Then I'm in a good situation and I have verified that this is really a Cauchy sequence. And now it's clear, we know the rational numbers. If somebody says, well, square root of 2 is not a rational number, then you already assume that it exists somehow. So it assumes that, I don't know, if you mark it on the line in a physical way, it is something which exists, but or you plot a square, you draw the diagonal, and you're saying, well, according to Pythagoras, the length of this is square root of 1 horizontal plus 1 vertical, so it is square root of 2. So this is the length of the diagonal of and then the question is it a rational number? And well, formal proof analysis courses is no, it's not a rational number. Whenever you would write it as P over Q, you get contradictions. But we all know you can approximate it. So what you're doing, you're trying, well, 1 squared is definitely too small, 2 squared is too big. So it must be between 1 and 2. So let's try 1.1, 1.2, 1.3. And so, of course, you find out it's 1.4 is still smaller as a square, which is less than 2. 1.5 is bigger. And you go on and go on. So practically you would say, well, what is he telling me? He's explaining how to get more and more digits of the decimal expression of square root of 2. But I would say I'm pursuing in some way, because we are all used to the decimal system and a Cauchy sequence. If we wouldn't have our 10 fingers, but maybe 12, we might use a different number system, or we could use it in binary system. We might like rational approximations. In such a case, we would choose different Cauchy sequence, always the same limiting element, and even without knowing that it exists, we could determine that there's a Cauchy sequence, and we could build up the real number system in that case from the rationals by taking equivalence classes of Cauchy sequences. So we have many Cauchy sequences representing the same number. In a Banach space, you may have many Cauchy sequences representing the same element, and therefore you define an equivalence relation. But I don't want to go too much in this direction, just mentioning that the best way to choose one representative if you are just going by numbers is to say, well, real numbers are infinite non-periodic decimal expressions. In this way you avoid the uniqueness problem, the problem that 0.99999 is the same as 1. If you say, well, 1.00 is clearly periodic, therefore, okay, sorry, I was confusing myself now. So I think one should use the non-stopping representation. Okay, maybe I should leave out this example. Now, I have already mentioned, and because it's here, I continue with this proposition number 1. That's the the corresponding definition. If we have a size measurement, we also have a distance measurement. The distance has similar properties immediately following from the 3 properties of this. If the distance between 2 objects is 0, they are equal. The distance obviously is a symmetric thing. So in this case, but also in the abstract situation, it has to be. It's an axiomatic assumption. And the distance coming from the norm has these natural symmetry properties. And also the triangle inequality has to be true in any metric space. So we have all these properties. And because we have derived this metric from taking distances, the difference between v plus x and w plus x is, of course, v plus x minus bracket w plus x, which is v plus x minus v is the same as distance between v and c. So this is giving us a translation invariant norm. Maybe, oh yeah, no, I can go on here because the main symbols that I want to introduce for this course are already here also. So definition 6 is the following. I'm using the symbol CC of RD. And CC has 2 letters C. The capital letter is standing for continuous. So the continuous functions with extra decorations are collections of continuous functions. The thing in the argument is the space where they live. If I would put their interval 0, 1, you would say I'm looking at the continuous functions on the interval. If I put RD, then you have to think D is the dimension. So mostly we will deal with D equals 1, 2, and maybe sometimes 3. So think of an audio signal as a continuous function on the real line. So then the parameter, the argument, which we in mathematics unfortunately write x, whereas in engineering, I'm aware of this, you write x of t. So you say x is a function of time. I'm saying, well, k is a function of the general variable. And since we are dealing with functions on RD, x, the elements x are in RD. But actually, I'm not caring much about at this point. You could give the same definition for other locally compact abelian groups. So if somebody has heard about periodic numbers, or if you like periodic continuous functions, you just have to change the domain and take the unit circle and so on. So we have the space of, and you see I'm using C here, the complex numbers. So we're talking about the continuous complex valued functions on RD. Now, once more, if I take D equal 1, these are complex valued functions. And complex valued functions can be thought in 2 different ways, and I will use both representations. One is to say, well, what does it mean something is complex valued? It has a real part, it's an imaginary part. The real, if you take, for example, a pure frequency, e to the I, let's say maybe I'm taking e to the 2 pi, e to the I, imaginary unit, or j if you are engineer, e exponent j 2 pi x. Then you will say, oh yes, this is according to Euler's rule, cosine of 2 pi x plus imaginary part, so I times the imaginary part, which is sinus of 2 pi x. These are the basic building blocks of Fourier analysis. They're periodic with integer periods. So if you shift the cosine of 2 pi x, it's going back to the original situation. So that's the advantage of accepting a 2 pi in the bracket, that your invariance property doesn't have a 2 pi anymore. And the other way to look at this is to say, well, every complex valued value of the function is a point in the complex plane. So I don't know, if I try to do it here, I hope you can see my mouse. If I think of some coordinate system here and I draw with my cursor a curve in the plane, then I'm actually showing you a function which is a complex valued function of the real valued parameter time. So again, stopwatch starting, 2 seconds, 1 second, 2 seconds, and that's the endpoint. So this is the value at t equals 2. I was starting maybe at 2 equals 1. And a complex valued function is a curve in the complex plane. Now, there's another little c here, and that's for compactly supported. So we mathematicians like to talk about compact support, but practically it means if you talk about functions on the real line, that if the argument is big enough, then there's nothing going on, it will be 0. So formally, I'm looking at for such a function, and the k, little k, is my standard letter for compactly supported functions. Actually, my advisor, Hans Reiter, was using a capital K here, but that's why I'm calling it little k. So k of x is non-zero. So I'm looking at the function and say, where is it living? I draw a function and I start with 0 and end up with 0. And then I take the closure, because if you have the sinusoidal function, for example, this spread out zeros or a polynomial, I mean, I don't want to exclude them. And if this is compact, so you have something like a bump function, it starts somewhere, it goes down, and then this thing should be compact, but since it's a closure of some set, it will be always a closed subset. So its set is bounded and closed in the real Euclidean space, if and only if it's compact. So if you like to think of a function for d equals 3, it just says, well, there's a box, a ball of radius r, or a cube of size s, such that all the values are only non-zero inside this function. So you could say, typically we're using this argument when we're talking about tomography. You're looking for the tumor in the head of your patient, and you're putting the body into the MRI scanner. And then, well, clearly the density of his head is a compactly supported function, because outside of the body there is just air which is not taking making any absorption. And so for a mathematical modeling of computer tomography, you're saying you have a function with compact support, and the support is actually, in this case, the material, the skin and the bones and so on, which are absorbing these X-rays. Okay, this is a space which is very nice, very beautiful. If somebody, I don't have to do a lot of details, if somebody is giving you 2 such functions and you make a linear combination 3k1 plus 5 times k2, you verify very quickly. Of course, the sum is 0 outside some set. I mean, outside of the larger of the 2 balls that the individual things have, you get still continuity. And so this is a linear space, but with respect to the subnorm that we will use, it will be not a complete space. So somebody could give you the Gauss function. The Gauss function is e to the exponent minus pi x squared, and we have seen the plots and so on, but it's non-zero everywhere. Even if x is, well, if you put it into MATLAB, e to the Gauss function at 10 or so is below numerical precision already, far. But for mathematicians, its exponential function of anything is a strictly positive number. So the support of a Gauss function is not here. So it's not in this family because it has infinite support. But of course, it's a function which decays actually extremely rapidly. It will be a prototype of a very nicely convergent function. And that means the limit of f of x equals 0. So the 0 is standing for vanishing at infinity. So I will talk about C0 of Rd, or of the function which are complex valued, vanishing at infinity. We will see in a moment, but I will suggest to take a short break soon. We will see that any such function is actually a bounded continuous function, because somehow it must be very small outside of some ball, and on every compact ball, any continuous function, according to the maximum principle, is having a maximum. So therefore, it's bounded at infinity, it's bounded on a big compact ball, therefore it must be bounded overall. Now, I would like to give you this proposition first, just to show you what we are having in mind for the next second part of this session. We will talk a lot about C0, but also about CB. Now, CB is even larger than the space C0. It's the space of all B for bounded. So it's the space of all bounded continuous functions, complex valued functions. And these bounded continuous functions are equipped with the sup norm. I will discuss the sup norm in more detail, but you can think of, well, I'm measuring the size of a graph. I mean, I have once more, a graph is something like this in the complex plane. And I say, well, if that's a very long curve, it's going on for infinity or so, but it's inside a ball in the complex plane of radius r. And if that is the minimal radius that I need to catch the ball, then I call this the sup norm. So it's just the maximum, actually, more or less. No, yeah, it doesn't have to be the maximum, but the sup over all the absolute values of the function that we can get from this function. I will give the formal definition. And then we have a number of statements. For example, we will show that C0 is a Banach space. So I will try to explain the abstract concept of a Banach space by mostly discussing properties of this. It's even a nice space with respect to an algebra, with respect to multiplication. And we can show that every function which is vanishing at infinity can be approximated by compactly supported functions. So it's the set of C0 can be viewed as the closure of these compactly supported functions inside the space of bounded continuous functions. And the main target, and before taking the break, the main target for the first part, I will see how far I will get, is to say, well, why are engineers interested in convolution? And the answer is, for me, because they want to understand translation invariant linear systems. And there was a series of papers by Mr. Sandberg who was saying, well, authors of books in engineering are cheating a little bit because they claim that every translation linear operator from CB into CB, any BBOS system, any bounded input, bounded output system, is represented by convolution. This is actually even an ongoing discussion, and I will hopefully be able to provide 1 or 2 articles to this subject during the course. But I found, and that's the starting point for the course notes, that one should look at the translation invariant operators or systems which map C0 into C0. I think this is the right starting point for the concept of convolution, even in the relatively abstract setting of convolution of bounded measures. And it's a way to prove basic results about Fourier transform theory. So to understand why the Fourier transform appears so naturally in the context of invariant systems. So we'll get a mathematical treatment of terms like transfer function and impulse response, which often is described in a little bit vague terms using the Dirac delta, well, object, measure, distribution, whatever. By the end of the course, actually, hopefully within the first 3 weeks, we will have a much more clear understanding of what the Dirac is and why it's relevant and what the shifting property of the Dirac delta impulse means and so on. So please stay tuned and let me take a short break of like 3 to 5 minutes, maybe 5 minutes, yeah? If somebody has questions, please let me know. So here you see there how to create a periodic function on the unit roots of order 480, starting with the zero vectors and making a random choice of coefficients on the Fourier transform side. So remember, when I use 21 coefficients, they start from 0 to maximal frequency 20. So that would be a cosine and sine with 20 full oscillations sampled fine enough so that you still can see nice curves. But then I take the IFFT, which means the FFT computes the Fourier coefficients of a given periodic functions. Therefore, the opposite construction is if I have such Fourier coefficients and only up to order 20, to maximal frequency 20, they are non-zero, and I make a function out of it, which is sampled here, but it doesn't matter. I see this complex valued curve. And if you go around, so kind of you say, yes, it's infinite, you go around in unit roots and you have certain values. And now what is the subnorm explained by this picture? You just say, well, how big does a circle have to be such that it includes all these things? So we could play around, take a circle, but roughly speaking, I think it looks like it would be a distance from the center to this. That's probably the maximal amplitude. And this is the subnorm of a function. So I'm going back now to the script file and hopefully. So now I hope that you can read the lines of the notes. If this is not valid, please let me know. So, and I would start slowly now with the definition that we have already seen, the continuous function with compact support. Since there is no protest, I think I can go on. So the support definition is take the values that the function has, where the values where it's non-zero, and the bar here is not complex conjugate, but means take the closure. So all the points which are kind of relevant for the function. Everything, a point is irrelevant if you can make a small interval, a small ball of radius epsilon, such that nothing happens around that point. Now, the simple lemma is an easy exercise. One is, are you in this space? If you have a continuous complex valued function, and the answer is if and only if just being outside of the ball of radius r means that the function has to be zero. And it's just in the background, the support is inside that ball, and the support by definition, you see here you have a closure, is a closed subset of a compact set, and that's always closed by basic principles of analysis. Now, I will talk a lot about operators, and we will very soon make use of these functions. Actually, yesterday you have already seen how you apply a translation operator to a polynomial, and it simply means you take the graph and you shift it around. as I like to say, the minus x is a little bit disturbing at the first sight, but at the end it's just exactly what you want to have. If you shift by 5 on the real line, you would like to know that the graph is moving to the right. And it's true if you're saying, well, take the new function and rename our functions f. This output of the linear operation f goes to tx of f. So the translation by x is, so that I call it the translated function, or the x translated function f. So it's the symbol in square brackets. So here, this one, which of course is just to help you at the beginning, later on we will read in this way, has values at any point, and you get the values of the shifted functions. Remember, I'm moving to the right. If I take the value at the new position, now going back by 5 steps, where the old position was and where I take from the original function. Now, it's important to know that it's not a tx applied to the complex number f of z, but it's an operation which makes out of the function f. In mathematics, we make the distinction f is a symbol for the function, and it takes the values f of z for z being one point in the domain. And there's a new function, and I call it tx of f. And of course, it's an assignment, it has values. But I can also say, no, I have a linear operator which maps, you throw in a function and you get out a shifted version of the function. And that's something which we will do all the time in Fourier analysis. Now, I have thought a little bit, and I was trying to avoid the so-called inverse head symbol, because some people use it for the inverse Fourier transform, so I use this check symbol. So it's f flipped. So the usual way I would demonstrate it in the live course is I would plot a graph on the overhead slide, and then I turn it around by 90 degrees, so you look at it from the other side. Or let's say if I have a function plotted on a graph, what you would see looking from the other side is exactly f check. Just for later on and for fixing some notations, but you have these notes anyway. We are learning to talk about characters, or in this course I will mostly talk about pure frequencies. In 2 dimensions we will talk about plane waves, so something which has shape like the ripples of a roof. Okay, so what is a multiplication with the pure frequency s? So first we have to understand what is the exponential function 2 pi I s x. Just think a one-dimensional case first. Well, take the real part of it, then you have the cosine of 2 pi s x, put it into GeoGebra, and make S a sliding identity, and you see how you increase the frequency by letting S go to infinity, and how it's getting more and more stretched as S goes to 0. So the world of pure frequencies have the parameterization S, and the only thing you should remember is if you have 2 dimensions, then this this s times x should be understood. You have it after formula 6 as a scalar product of the 2 variables, and then you're multiplying the pure frequency in the direction of frequency s1 in the x1 direction. You multiply it in the other direction with s2 and so on in multi-dimension. So that's really how you can describe a plane wave. Put a profile of format cosine of 2 pi s1x in the horizontal and s2 in the vertical direction, and then you make a plane wave out of it, and that's all you need. So these functions are so valuable and have so fancy properties. So sometimes I'm even saying, well, Fourier analysis grew out of the complex numbers, so that some people had this strange idea of introducing complex numbers. And you talk about real and imaginary part, and it has a little bit the taste of, does it exist, or is it an imaginary object which we just invent? I mean, nowadays we just say, okay, it's pairs of real numbers. We know real number exists. Pairs of real numbers have to have their laws. They're multiplying. So formally you adjoin the imaginary unit, but practically it's a rotation by 90 degrees in the complex plane, and the plane is concrete, rotation is concrete. So real numbers and complex numbers can be multiplied. You can switch from rational numbers to real numbers to complex numbers. Everything is fine. And even such a, well, incredible object like exponential function. So think this is an irrational real number with a complex, also irrational pi exponent. So this is meaningful. And the answer is yes, yes. It's like the ordinary exponential function, which we have seen so much in the recent days in the discussions about COVID. It's the same as when you're having biological growth, or if you go to your bank and you have the rates of increasing, or what you have to, how the money is changing also. So it's just the exponential function is a great thing. Complex numbers are a great thing. You can combine them and you get these wonderful pure frequencies, and it's up to us, let's say mathematicians and then engineers using it, to make out of it something which is useful, and as we know it's useful to do our mobile communication, to do data compression, to transmit data, whatever. Okay, so one of the goals will be, of course, the study of the Fourier transform, and just take first the one-dimensional case. So it's just saying, well, we have to be able to take the integral of the f against a complex exponential function, and the argument of the Fourier transform is this parameter s. So maybe again, take a function f which is compactly supported and two-dimensional, maybe real-valued function. So you would say, okay, this is a blob in the image plane, so it's just an image. And then you would like to know, can we compute this integral? And I would say, okay, if that bump function f is a continuous function, it's clearly Riemann integrable. You think of these little Lego-like upper Riemannian sums and lower Riemannian sums, so no problem. Make it finer and finer, and the limit you get some number and you call it Riemann integral. But even if you multiply with another continuous function, it's still vanishing outside of the box where the f is vanishing. So this is another Riemann integrable, and then you can do it for every s. So if you start only to deal with compactly supported continuous functions, and that's why they are quite useful to get as a starting point, we could describe using Riemann integrals already what the Fourier transform is under a specified setting. Now, of course, people would say, okay, the Riemann integral is not so good. It's not true that you can exchange the limit of functions in a pointwise sense and the integrals. Just to mention it as a side remark. A good example is you can take the rational numbers in the unit interval. Take all these rational numbers, they all can be written as fractions, and so you first verify that they're a countable system. So you can label them with 1, 2, 3, and you can cover all these things in a piano-like curve. And then you're saying, well, I take a function which is 0 at the first 500, 501, 502 functions, rational numbers. Now, each of these functions is clearly Riemann integrable because you can make these boxes very small, and they will have integral 0. But if you take these countably many rational numbers, we know that rational numbers are dense. So if somebody tries to put a bar above them, then because of all these irrational rational numbers where the function is now 1 in the limit, you cannot put it lower. If you are coming from below, you have a lot of irrational numbers, so you can have lower sums and upper Riemannian sums never match, and so in the limit the function is not Riemann integrable, and that's why I would say, from almost unjustified from my personal viewpoint, the Riemann integral has been put down for, at the time, And since 100 years, we're using Lebesgue integration theory, which in a way is very good, but it doesn't help us, for example, to find out, I mean, what is the Fourier transform of constant 1? I don't know, but I think some engineers or physicists would probably argue like this. Okay, we look at the integral for s different from 0, then these are oscillatory functions integrated against 1. Well, just make it longer and longer, so in the mean you get probably 0. Okay, but then you're saying, well, but take s equals 0, an exponential function with exponent 0 is just 1. F is constant 1. So you're integrating plus 1, and then you're saying, oh, yeah, it's plus infinity. Okay, now I understand why the Fourier transform of constant 1 is the Dirac delta. It's the function which is 0 everywhere except at the origin, but at the origin has the value plus infinity. But this argumentation is clearly, at least at most, a heuristical one, because what if I replace constant 1 by constant 5? I mean, I would expect as a mathematician that you get 5 times Dirac, and that's actually what we will get in our calculus or so. But if you take this naive approximation, I would say, okay, 5 times this infinite, 5 times infinity is just infinity. So it's the Dirac, independent of how you rescale the constant value, whether you take 3, a constant 3, constant 5, constant 700. It's always, as long as you take a positive constant, it's always the Dirac. And that's simply not true and not good. So what we will see how to do it is a way which tells us why we get 3 delta when you have constant 3 and so on. And so we just extend this naive or simple-minded integral transform to a transform which gives the meaning for the Fourier transform to many, many more general property objects and so on. Now, I will later on work with convolution, pointwise multiplication or so, and this is something that you should look up later on, but I would like to mention it at least, is that when we mix operators with multiplication symbols, for example, then if you see a chain of symbols like TXF multiplied with G, you might be tempted to interpret it as, oh yes, f times g is the product function, like sine squared or so, and then you shift it. Or you're saying, no, the tx is applying to the f, and then you're having a shifted sinus function multiplied with an unshifted sinus function. Whenever there is an ambiguity, I mean, if you see an ambiguity in the script, please tell me that this is ambiguous for you. Then I will either correct it in the script, and most of the time I try to put brackets where I think it's dangerous to leave them out. But on the other hand, I try to avoid as many brackets where it's not necessary. So we will have convolution, and of course many of you know already what convolution is. And I will absolutely avoid symbols like h convolved with g multiplied with f, because it can be 2 absolutely different things. First you multiply out, and then you multiply convolving sense, and then you multiply or in the other way. And there is no associativity law if you have 2 different kinds of multiplication. So of course you can say multiplication binds stronger symbols attached by multiplication should be first computed and then addition. But if you have 2 kinds of multiplications, one has to be more careful. It's also important, and that's what I have already mentioned, that I'm not talking about a shift operator applied to a function value. And that's why the engineering terminology or description of functions is a bit problematic from my point of view. Or maybe I should put here, normally an engineer would write, well, this is the function named f of t minus x. But of course, this assumes that you know that x, unfortunately, mathematical x, is the shift parameter and the t is the function, because you're always thinking that t is the continuous variable. That's like GeoGebra is assuming that x is the name of the variable or so. But I'm not, I mean, if I would say I take the engineering description of a function and write f of t, and then I apply the t of x, it looks for a mathematician like I have a number. For every t, there is a number, and I apply the number, the shift operator to the number, and that would be nonsense. So we have, I think, just think of the graphs, and we have certain properties of the operation that we have here. Now, I'm going on. Yeah, I don't go through all these symbols, but maybe mention that during the very first month or so, you will learn all these operators. So we have seen the translation operator and the modulation operator, which is also called a frequency shift. We have the flip operator, and applied to a function and not to a set. The bar means conjugate. So if somebody is saying, I'm taking a function and make a star, then for me, it means I take the flipped version of the function and then I take the conjugate. We will see more of this and discuss more of this. But formula number 2 is something that you probably have seen. It says that if somebody applies the modulation operator to some function, so think of a sequence which represents a sound signal, and we modulate it with a pure frequency, and then take the Fourier transform, what you will see is that you get a shift by exactly the parameter s. So you multiply with frequency 5, then the Fourier transform of the modulated operator, of the modulated thing, is just the Fourier transform of the original one, but shifted by 5. So that's what you would get from your keyboard when you hit the transposition key. It's nothing else but a frequency shift. So that's why modulation is viewed as frequency shift. And if somebody wants to get familiar with these things, you might want to look at this somewhat well, strange or exciting or important property. We'll use it also. It's the question, is it the same to take a modulation first and then a shift, or change the order? So look at the left and right hand side here. The difference is just the order of how you apply it. And you see the difference is just the multiplication with some number, and this number has to do with the ingredients. So it's the if modulation comes first and then you shift it, then, well, what you have to think of, if you realize it, I mean, you have to say, well, what is this operator doing? You apply it to a function. Well, what is the resulting value of a function at a given point, and so on? And you find out that a modulated function is something where you multiply the function with a pure frequency. Now, if you are doing it in this order, you are first multiplying with a pure frequency, and then you're shifting. If you're doing this operation, you're taking your function, and then you're multiplying with then you're shifting the function, and then you're multiplying with frequency s. Whereas on the left-hand side, the frequency is also shifted. It's not shifted on this side. And therefore, you have to look what happens with the frequency if you shift it. And that's a very nice example for the exponential law. You just have to apply the exponential law. So I think verifying this, I would say, try to give yourself like 5 minutes to prove it. If not, start 2 hours later or so. And if not, try it a few times. It's worthwhile. You should do it once because you should do it yourself. Mathematics is not a watching sport or so. Because then you can appreciate the usefulness of such a formula. I will use it a lot. Maybe even later on I will show it to you, but please try it and then you can appreciate it. Okay, now I will jump. This was, yeah. So I will now, there was a gap, oh, here is it. So the main point of the rest of this lesson is about the sup norm. So I told you that the sup norm is the size of a continuous function, and if it's bounded, it simply means the graph is sitting inside of some circle or maybe some square, and you measure it in this way. And the first statement, which I even didn't write down, is the fact that you're having a vector space. So if somebody is giving you two bounded continuous functions, the sum of those bounded continuous functions is bounded and it's continuous. And of course the norm is satisfying the triangle inequality. I mean, how big can f1 plus f2 be? I mean, of course, at most as big as f1 is at that place plus f2 at the place. And actually, if they are happening to have the same maximum at the same, if they happen to have the same, let's say, positive maximum at the same place, then the sum will have the same norm as the sum of the norms. Otherwise, the norm, the sup norm of f1 plus f2 will be at most, will be not larger, will be strictly smaller actually than the sup norm of the first component plus the sup norm of the second component. So it's very easy to verify that this is a vector space with respect to this norm. So, and I told you, if I want to do approximation, I'm saying a function is close to the other function f if there's an epsilon strip. So you just take the graph of the function, make the copy with f plus epsilon, f minus epsilon, and then everything which is inside this graph will be fine. Now, I must say, I realized that I should give a little bit more illustrations, but the next thing is a space of uniformly continuous functions. So I call it UB, so uniformly continuous and bounded functions. And I just realized that I should add the definition, the usual definition of uniform continuity. Let me try to explain it by some harmless demonstration or so. If you have a triangular function, then of course it's a continuous function, and let's say the side step is 45 degrees. Then if somebody says, well, I'm giving you some epsilon, and please tell me what is the size of the interval delta, such that you can guarantee me that change by delta in the argument doesn't make more effect than this, then you would probably say, oh, I can take delta equals epsilon. If the steepness is increasing, then you would maybe say it's now twice as steep, then maybe I have to take a smaller value of delta. I may take, I don't know, let's say 3 times as steep, then I would take delta 3 epsilon divided by 3. So I make an interval which is much shorter, but still I would be able to guarantee. Now, when do you say a function is continuous? Well, this is a global statement. It's formally a statement saying, well, it's continuous at every point. So if you tell me I want to test the function at this point x, and you're telling me that my epsilon is so and so, then I will find a delta depending on where you point out to me that you would like to measure it. Maybe you remember yesterday we were looking at the function of the chirp signal, which is in the real part, it is cosine of x squared. So it's a function which is going down and up and down, and it's starting to increase and increase and increase anymore. Now it's clear if you're giving me an epsilon interval and say, well, given the point and the epsilon, is it continuous here? I would say yes. Is it continuous there? Yes, yes, yes. But the further you go to infinity, the more I would have to shrink my delta. So such a chirp signals would be an example of a function which is continuous, complex valued, but not uniformly continuous. You would have to tell me where you want to test if I'm supposed to find a delta. Uniform continuity is making the same thing uniform. You're saying, well, or let's say I like to have this role game. I claim if some function is, let's say, pure frequency is uniformly continuous. maybe that would be a good example. Pure frequencies, they're not decaying at infinity, but they're uniformly continuous. And what does it mean? Well, you could give me any epsilon, and I would have to find some delta, which is so good that you could apply it anywhere. You don't have to tell me or where you will do your test. You keep it secret, and you're saying, okay, I would like to test your function whether it's really uniformly continuous. I'm giving you an epsilon, a very nasty, tiny epsilon. Now, I know how to prove it, but let's just go for the psychological part of the story. That it's uniform continuous. So I'm doing my calculations. I look at the derivative of the function and say, okay, the steepest parts are such and such. So I'm giving you a delta. Of course, if you give me a high frequency, pure frequency, S is big, then maybe I have to choose a quite small delta. But once the function is fixed, I will be able to find a delta. And then I say, oh, okay, come on, test it anywhere. Test it at x equals 5, x minus 20 or so. You should not be able to find out a problem, which means a problem for me, 2 points at distance delta, where still the arguments are further away than epsilon. Recall this chirp signal with the cosine of x squared. Whatever delta I would get, you would choose a point very far away, close, going to infinity. You would say, come on, even with the tiny delta, I find 5 full oscillations. So there are 2 values, one is +1, the other is -1. So chirp signal can never be uniformly continuous, which is one direction, and the other is pure frequencies, for example, are uniformly continuous. Now, I like to have observed that the definition, and it's more or less the proof here, I will not go through the details, but it's a good exercise in the notation and in the symbols, what they mean and so on, is the following. If somebody is giving you a function which is a bounded continuous function, so it only means that f is bounded continuous, tx of f is bounded continuous, so it's reasonable to measure the size. The difference, we're in a vector space, the difference is a bounded continuous function. So this is certainly a valid statement or so. And I claim that the subspace, it's actually a subspace of a uniformly bounded continuous function, is belonging to the space. Subspace is the same as to say, if you check what happens if you compare the function with the shifted functions. And if this is small, whenever the shift parameter is small. So what does it mean? It means kind of, when is this condition 12 okay? It says, you're giving me or what is the test that you can apply? You take the f, and then you look at the maximal deviation between tx of f and f for variable x. You look at letter x go through the range, and then you measure it and look how it behaves when you make x smaller and smaller. If it's enough to be close enough to 0, so maybe less than 0.001, and all the other values which are smaller, all they satisfy that this is smaller than epsilon, then you're having a uniformly bounded continuous function, and vice versa. So this is really a criterion. Just think of, again, this chirp signal, try to shift it. Well, for every tiny shift parameter, at the place where the oscillation is already extreme, you will find a place where the value f will be +1 and the shifted version will be -1. The difference at that one place will be already 2, so the supernorm does not go to 0. So that would be another argument to prove that chirps are not uniformly. You see here, I mean, just point out this game with the logic that you're saying for any given epsilon, there is some delta, blah, 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 has to be used and it will be combined. I think it's not important at the moment to go through the details. But if you try to read the proof or so, feel free to comment to me, because maybe what is kind of plausible to a mathematics student is not plausible for you, or maybe some definition is missing, but I will work with this characterization. So you can say, I take it as a definition. I don't care about the classical definition. For me, CUB means that I have the property 12, and that's fine with me. What is interesting, however, is the fact that or what you can do directly if you take the classical definition or this definition, of course both will give the same result, is to show that this is also a vector space. So it's actually, as we will see later on, it's a closed subspace. So if you take a limit of uniformly bounded continuous functions, then we'll also have this property. And if you even multiply two uniformly continuous functions, it will be uniformly continuous. That's not so surprising, actually, because you, of course, remember that if you take a continuous function and you multiply with another continuous function, it's a continuous function. Now, that means that for every given x, you have this epsilon delta game. And now it's just saying, now if the same delta is coming out for the same epsilon, independent of where you test, so it's not really a new proof. It's more or less the argument that you need for multiplication of continuous function is continuous. So very often you say, I don't know, why is x to the 5th power continuous? Well, x is a continuous function, obviously. X squared, x third power, by induction, they are also continuous because they are products of continuous functions. Okay, the next statement is lemma 2. Now, lemma 2, number 2. C0 is a closed subspace of the uniformly bounded continuous functions. So this has two statements built in. One, it is, of course, that it is inside first. So is it true that continuous functions vanishing at infinity must be uniformly continuous? This is not completely obvious, but plausible once you have learned the theorem which is done in analysis, which says every function which has compact support or which is living on a compact set which is continuous is uniformly continuous. Just, I mean, my understanding of the intuitive understanding of this situation is the following. Assume you have a function on the unit square, so on -1, let's say 0 to 1 squared, so you're really on the unit square. And you have a function which is continuous there, but not uniformly continuous. So just if you try to prove, to understand it by reading or listening to me now, maybe it's not so easy, but what does it mean? It's uniformly continuous. It means that for every epsilon, there's a universal delta that can be applied to every position. What is the logical converse for the existence of a universal delta? Saying, well, it's continuous, so it's true for every point there is something, but unfortunately it's not universal. Assume indirect assumption, it's not universal. So you can find for for some nasty delta, it's maybe very tiny but still positive, there is a problem with the universality. I can find a pair of points which are at distance delta 1, at delta 2, and you make delta n smaller and smaller, and you will always find pairs which are having the problem that the points are close, but the arguments are far away from each other. Well, but then you use the Heine-Borel property and say, well, but if somebody draws infinitely many points in the unit square, and it's now the compactness argument, they must converge. I mean, you cannot, I mean, that's catch the lion in the desert. You would take the square, cut it into 4 pieces. If there are infinitely many points from the beginning, at least one of these 4 pieces must contain infinitely many points, and you continue and continue. So in this way, you find every sequence in a bounded or compact domain must have a convergent subsequence. Okay, so these pairs, they're gluing more and more together, but also they are convergent to some points. Because they're gluing together, everything, all the trouble is concentrated in some point. And now, of course, you know, there is no point which is a troublemaker. So you derive a contradiction. You get that because the function is really was assumed to be continuous at every point, not with any single exception. Therefore, such a troublemaker point cannot exist. Therefore, the indirect assumption of problem with universal delta is not okay. Therefore, a function living on a compact with compact support will be uniformly continuous. So this is an argument that I have tried to indicate a little bit in 2D, and now you can go through the same argument more or less. I mean, I will not, probably I just will try to come to an end here. You can say now every function in C0 which is vanishing at infinity can be approximated by functions which have compact support. So roughly speaking, well, if you're willing to use 1/2 epsilon to replace the original function by compactly supported, that compactly supported function must be a nice function. It will be uniformly continuous. And that allows you to transfer with another epsilon over to the uniform continuity to C0. So yes, it's true that we have now 3 different spaces. You have them here in the graph. It's the C0 space, which has this also nice property that's a Banach space. So if somebody says, I have a sequence of functions, all of them vanishing at infinity, and they are uniformly convergent, so they are a Cauchy sequence with respect to this norm, then the limit will be also continuous and will vanish at infinity. Each of those functions, I mean, this is a space which is, for us, the most important space. Each of them is sitting inside the uniformly bounded continuous functions, and each of the uniformly bounded continuous function has the same limiting properties. So limits of uniformly bounded continuous functions are uniformly bounded and continuous, and they are sitting inside all of the bounded continuous functions. And clearly, there's strict inclusions. So we had already the example, I don't know, chirp. Now, pure frequencies are not decaying at infinity, but they are uniformly bounded and continuous. So there are examples that the first inclusion is a proper inclusion. Chirps are an example which are bounded continuous, but not uniformly bounded and continuous. And therefore, we have really 3 different spaces, all equipped with the same norm, each of them being closed. So you can have Cauchy conditions and you will not leave either of these spaces. And finally, my comment is we will discuss the multiplicative structure. If somebody is multiplying a bounded function with a function vanishing at infinity, so assume somebody is multiplying a C0 function with a pure frequency. Pure frequency is bounded and continuous also. Well, clearly the product will be also small because boundedness plus small, some fixed constant multiplied with a small constant will be small. However, if you multiply a continuous uniformly bounded function with a bounded function, you will not preserve the better property of uniform boundedness. Just take the example that uniformly continuous function could be constant 1. So multiply constant 1 with maybe a chirp signal. We've seen chirp signals with constant 1 is a chirp. It's only bounded continuous, but not uniformly continuous. So this big guy with this very small guy multiplied allows us to get into the small guy and therefore, of course, stay in this space. But this guy doesn't allow multiplication from the big guy. So the only thing that you can try, and that's again working as I mentioned, multiply 2 uniformly bounded continuous functions, then you will get uniformly continuous functions. Okay, I think that's more than enough for today. And I will try to do a few things, prepare a few things with MATLAB for Tuesday. So I'm not sure if, I think it will be a good idea to mix theoretical and applied things. And the goal of the theory part will be more or less the next step. How can we identify the impulse response of a translation linear or an invariant system understood as an operator which maps C0 into C0? So we will work mostly with C0. And so thank you for your attention. And if you have questions, I will turn off the recording now and feel free to ask.